Continuing on here, you have a diagram that shows or emphasizes the intercalated disc that you find in cardiac muscle. And so here you have this section with the intercalated discs, and they're definitely providing this direct electric connectivity from one cardiac cell to the next. Here is a comparison table of the 3 different types of muscle: skeletal, smooth, cardiac muscle. Be sure to review that. We spent a whole chapter on the skeletal muscle, and that was the same table that you saw there. It's table 12.3 from the muscle chapter. Okay, so now let's take a look at how cardiac muscle is doing the excitation contraction coupling. Very brief review from the skeletal muscle. So in skeletal muscle, you need the release of acetylcholine from an axon terminal, and then the acetylcholine binds to the acetylcholine receptor, and that will open an ion channel. It's a cation channel that lets positive charges in, and that causes an extra potential to travel down the sarcolemma of the skeletal muscle cell. It will go down a T-tubule. It will open the DHP and ryanodin receptors, which then are releasing calcium from the internal stores, and that ends up binding to a troponin, and then tropomyosin will move off of the actin, and then actin and myosin will interact, and you get the cross-bridge cycling. So keep that in mind and take a look how similar this is here in cardiac muscle. So we are starting out with a pacemaker, the pacemaker sending a signal down these myocardial cells, and here comes this extra potential traveling down this depolarization wave. And here, instead of the DHP receptor, we have a very similar type of receptor. It's called an L-type calcium channel, and that will open up. It's linked here to a ryanodin receptor, which is very similar. It's basically identical. Here's your sarcoplasmic reticulum, the calcium storage place. So as soon as the ryanodin receptor opens up, we get the calcium coming out. The calcium then will lead ultimately to the contraction, and basically the same setup as before. Once you pump the calcium back into the internal stores right here, and this will have to require some ATP because you're going now, you don't have another concentration gradient, you're going against a concentration gradient, and you can also pump some calcium outside of the cell. Okay, so that will lead to relaxation in steps here. So the actual potential is traveling down the myocardial cells, the surface of them, the membrane here, and now the actual potential will go down this T-tubule and will open up this L-type calcium channel. This is a voltage-gated channel, and it will open up. It will also, it's linked to this ryanodin receptor. It will open up to ryanodin receptor, and the calcium from this sarcoplasmic reticulum will leave, and so calcium is coming out. So calcium coming out here, they have it drawn in. The calcium is now, the calcium concentration inside of the myocardial cell will increase, and that will cause the binding of calcium to troponin as before. Once the troponin changes the shape, then there's no more holding back, that the myosin heads will interact with the actin, and that causes the active shortening and then ultimately the contraction of the muscle. So we have the contraction right down here happening. So here, sort of everything put together right here, and the calcium, the troponin binding to calcium, that is the signal that now actin and myosin can interact with one another, and the whole thing will stay contracted until we are removing the calcium. So now we need to get busy and putting the calcium back into the stores where it came from. So we need to pump it back into sarcoplasmic reticulum stores. That will cost us a little bit of energy. Right here you can see there's the expenditure of energy for all of this. We will also pump some of the calcium. It's pumped outside of the cell, that's up here, so we're going to get rid of some calcium this way too, and then we can relax. Now the calcium will come off of the troponin, and the troponin, the actin and myosin interaction will stop, the muscle will relax, calcium is being pumped out or back into the stores, and then relaxation comes in. Now, the strength of a myocardial contraction can be graded. That means there is a stronger versus a weaker kind of contraction, and the force generated is proportional to the number of active cross bridges that are participating, and that depends on how much calcium is bound to the troponin. It also affects the sarcomere length, affects the force of contraction as well. Now, moving on to a very important slide here in this lecture. We're going to take a look at the actual potential of a myocardial cell. So, flashback to the nervous system. The nervous system actual potential the beginning here looks similar. So we're starting out with a resting membrane, and then we're shooting up to a positive value on our membrane potential because of sodium influx. So once we reach threshold, and the sodium channels, the voltage gated sodium channels open up, and that's the same case here. We're shooting up to a positive value, and then we are decreasing the permeability to sodium by closing the inactivation gates, or putting them in place, I should say. So now here, once we are up here at plus 20, you have an additional player coming in, and that means it's not just the potassium channels that are now opening up and that are bringing the actual potential here back down, or the membrane potential back down into the negative, and eventually even in hyperpolarization, and eventually back to resting membrane. But you have two ions here, and these two players here are potassium and calcium. Now, potassium is in high concentration in the inside of the cell. So if we're opening the potassium gates, then positive charges will leave the cell, and that should bring our membrane potential back into the negative. Well, problem is here we're also opening calcium channels, and these calcium is in higher concentration on the outside of the cell. So if we are opening the calcium gates, that means we're going to have calcium, which is 2+ with the charges, and we're going to have calcium coming into the cell. And as the potassium is leaving and the calcium is coming in, the two of them, they duke it out for quite some time. And that's why you're ending up at this shoulder right here. So it's basically, I call that the battle of the cations. Potassium is leaving, calcium is coming in. And so the two balance each other out for quite some time. And eventually the permeability of potassium increases and the permeability of calcium decreases, and so then potassium wins, and we're coming back down here. So let's do this in pieces one more time. Our resting membrane potential is more negative than you would have with a regular nerve. So here they're putting it at about -90. That's quite polarized, quite negative, but anyway, let's leave it at that. That's fine. So our resting membrane potential here is starting at -90 millivolts. For a nerve action potential, we were at -70 millivolts, but it's okay. So now we need to reach threshold, and that threshold is basically determined by the pacemaker cells that are sending a signal. And then once that signal from the pacemaker is arriving, then the voltage-gated sodium channels will open up, and the membrane potential shoots up to +20 millivolts. Once this has happened, then we're inactivating our sodium channels, and now we're opening up potassium and calcium channels, and they're duking it out for some time. So they're battling it out with potassium leaving the cell, calcium coming into the cell. We're creating this shoulder. And this shoulder is very important because we need to make sure that the depolarization wave travels through the entire myocardium and is then followed up with one forceful contraction to pump blood out of the ventricles. So we need to have this shoulder in order to allow the time to travel throughout the entire myocardium. And eventually potassium wins. We're going to have a lot of potassium leaving the cell, which brings us back to our resting membrane potential all the way back down to -90 millivolts, and then we can start over. So please make sure that you understand this slide, especially this part right here, and that you know the difference between the myocardial action potential versus the nerve action potential. So here in pieces, all starts out that we are receiving a signal from the SA node or the pacemaker in general, and that opens voltage-gated sodium channels. sodium channel, the sodium permeability increases. We're going to hit a peak at plus 20 millivolts here, and then the sodium channels inactivate, opening up potassium and calcium channels. At first, the calcium permeability is more than the potassium permeability, and so you're gonna duke it out here for some time. This creates this shoulder right here with this plateau phase of the myocardial action potential. Eventually the permeability of potassium keeps increasing and calcium is decreasing, and so now the potassium, the leaving of these positive charges from potassium, brings down the membrane potential all the way back down to minus 90 millivolts, where we're going to be at rest again. So then we have reached the resting membrane potential again. Let's take a look at the timing of all of this. And what you have here is superimposed a myocardial action potential, where we have on this side in red the membrane potential that starts at minus 90 and then goes up to plus 20, and then we have this shoulder, this plateau phase, and then we're coming back down. The timing of all of this is about 250 milliseconds, so a quarter of a second. And by comparison, the nerve action potential was only 2 milliseconds. So the myocardial action potential is very, very long in comparison. Now here, superimposed in blue, the tension as it develops in a skeletal muscle fiber. So you would have the rising phase, the muscle contraction, and then muscle relaxation. We put the entire time frame of a muscle twitch at about 200 milliseconds, so about the same length as the myocardial action potential. And so you get a feel for the time frame of it. So it's very special that the myocardial action potential has this plateau phase that makes sure that the entire myocardium will be depolarized before we go into contraction. Here's another thing that's special about cardiac muscle, and that is a very long refractory period in cardiac muscle. So to prevent a tetanus, a long sustained contraction, you would not want that in the heart. Here they're putting the refractory period at 250 milliseconds. So while the heart or these myocardial cells are going through an action potential, you cannot get another action potential and a response from the muscle. So the muscle has to go through the whole program of this depolarization, and it's refractory to another stimulus. That's very important. It also has implications, of course, for the maximum human heart rate. Max human heart rate, max HR for humans, is equal to 220 minus your age. And so that means if you take a look at this here, theoretically at least, if you can get one action potential followed up by a contraction every quarter of a second, so every 250 milliseconds, so technically there would be 4 times 60 seconds to a minute, so 4 times 60 is 240. That would be the theoretical limit that the human heart can achieve. Practically speaking, the maximum heart rate that you can achieve, the rule of thumb, is 220 minus your age. Let's quickly take a look at how skeletal muscle is refractory, and you can see here that the refractory period, this is just a yellow highlighted area, that's a very short time frame. That's then followed up, of course, the stimulus is followed by contraction, but you can see how skeletal muscle easily can right away get another stimulation, and that would mean that we can have multiple stimulation, which you can see as the staircase effect, and then you can even have an, you go up and then you have an incomplete tetanus or a complete tetanus. It would look like this. The heart, obviously, you do not want it ever to go into a tetanus, incomplete or complete, and either way, you don't want that. Now let's take a look at yet another type of action potential, and that will be the action potential of pacemaker cells. They're also called autorhythmic cells, and basically what they're characterized by an unstable resting membrane potential. They don't spend any extended period of time at here's minus 60, that will be their resting membrane potential, but right away leak channels will allow calcium to come into the cell, and that brings it to the next threshold at minus 40 in this case here very quickly, and then they will fire another action potential. Then they come back down, and they will spend a brief moment at rest, but then right away they're going into another, the calcium moving in gets them back into threshold, and then there they go again, and basically they will fire at a certain rate. In humans, the firing rate of these action potentials is about 70 beats per minute, so 70 times per minute approximately.